So when you're going to be having a chemical reaction happening over here, the salt bridge over here is going to be talking about the separation over there. It is going to be talking about how to connect the separation. And you're correct over there. The salt bridge is something which is going to be disrupting the, it is helping the flow of electric charge go more smoothly. So why is the salt bridge necessary? The salt bridge becomes necessary because when you end up having an anodic half cell and a cathodic half cell, in this case here, let's take the zinc itself. So this is going to be a zinc rod dipped in a zinc 2+ solution. Okay, now, and the next thing is going to be here, we are going to be having a copper rod dipped in a copper sulfate solution. You'll be having a tiny bit of dilute H plus here, you'll have a tiny bit of dilute H plus here. Okay, so when you're going to be having this as a situation over here, what happens now? So in this particular case here, you're going to be having these two being connected by the cell. So there will be a bulb here. I suppose I should have drawn it a little bit better, but chalo, a bulb will be over here. And we'll end up having this as the cell. Okay, so you're going to be having this as the cell here. Now, when you end up having the reaction happening, you're going to be having zinc 2+ here is going to be produced as the zinc rod dissolves in. So as the zinc rod is going to be dissolving into the solution over here, what is actually happening is going to be that you're going to be having in this solution here, zinc +2 concentration keeps on increasing. Okay, it keeps on increasing. Okay, so if it keeps on increasing, what is supposed to be happening here in the process? The zinc is supposed to dissolve and become zinc 2+, and it should kick out electrons. Those electrons are supposed to flow through this circuit. When I turn the switch on, those electrons will flow through the circuit over here and they will reach this copper electrode. So far clear?
Yes.
And if they are basically going to be reaching the copper electrode, then the bulb will glow. That's the idea here. So now when they reach the copper electrode, what is going to be happening in this particular case over here? The copper part over there is going to be the copper +2, which is present in the solution over here, is going to be accepting the electrons, which are going to be coming through the copper rod over here, and they are going to get deposited onto the copper rod there. So we're going to be having the copper 2+ getting deposited and becoming more copper and getting added onto the copper rod over here. That's effectively what happens. So if this is going to be happening here, let's now try to see what is going to be happening. Let's try to let this go, let this happen for some time. So if I let this happen for some time now, what's going to be happening is very simply put, in this case here, zinc 2+ concentration, as I said, will keep increasing. And as the zinc 2+ concentration keeps increasing, this entire region will effectively become positively charged. Yes or no, Kana?
Yes.
So if this entire region becomes positively charged, will it not pull back the negatively charged electrons that are trying to escape?
Yes.
Right. So in this particular case here, how do I measure the voltage? Let's talk about that quickly. So how I measure the voltage is I will now put a voltmeter here in parallel to this entire thing. So when I put a voltmeter in parallel like this, what is that voltmeter actually going to be measuring over here? Tell me, what is a voltmeter measuring?
The potential difference.
What does that mean? What does that mean? So what is it measuring?
The voltage.
Okay. What did I tell you electrode potential is just a while back? Why did I go into tangents 2-3 times till now? What is the story I'm trying to explain here? What is a voltage measuring? It is measuring the tendency of that chemical reaction to happen. Correct? Yes. So
Yes.
I'm going to be having at the start, I will have some E value. Let's call it E naught. No, let's not call it E naught, E1. Okay, I'm going to call it E1. Okay, so if I'm going to be having E1 as the what do you say, electrode potential of this circuit, no salt bridges here by now at the starting. What will happen if I turn the switch on? The first measurement is E1. What will be happening then? My zinc 2 plus will get accumulated on this side, correct? So this side, zinc 2 plus will keep getting accumulated. Positive charge
Yes.
keeps increasing. That will pull back the electrons to some extent, correct? So what
Yes.
is this voltage really measuring? It is measuring how easily the electrons are moving from one end to the other. That is what it is measuring, correct?
Yes.
So when I say tendency of the reaction to happen, what does tendency of the reaction to happen mean? Tendency of the reaction to happen basically refers to nothing but what is meant by tendency, or other you can think of it as tendency only again over here. So tendency of how smoothly tendency of how willingly would be a better way of looking at it, how willingly electron flow happens. That is basically what we are measuring over here, correct? So if the electron flow is happening more willingly, I'm going to be having what is called as a higher voltage, correct?
Yes.
If my electron flow is happening less willingly, I'll be having lower voltage, consequently,
Yes.
right? So now in this particular case here, Kana, come to this, what is going to be happening? As my zinc 2 plus gets accumulated here, what will happen?
Voltage will decrease.
Voltage will decrease sharply because that's going to be pulling the electrons back. Same thing over here. In this case here, what will be getting accumulated in the solution? What will get accumulated here?
Copper.
Copper 2 plus is leaving. What is it leaving behind? That will get accumulated now. What is the copper 2 plus paired with in the beginning?
CO2 plus is accepting electrons.
What is the copper 2 plus paired with in the beginning?
Copper rod.
Copper 2 plus, Kana, what is that guy's partner in the beginning? At the starting, before the reaction happens, before I turn on the switch, who was the partner for the copper 2 plus? The sulfate. So when the copper 2 plus is getting deposited and becoming copper, who is it leaving behind?
SO4.
So in this case here, SO4 2 minus accumulates. So you're going to be having negative charge getting accumulated here. So effectively, just as much as this side. On this side, the zinc 2 plus will try to pull the electron back. Here, the negative charge accumulation which will be happening will push the electrons away. So you're going to be having both sides are going to be rejecting the flow of electricity. So the voltage which you are going to be having will drop very, 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 very fast, and the cell will not work. All right, the cell will stop working very, 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 very fast. So that is the reason why people have to use a salt bridge. You understand what's happening over here? Why a salt bridge is necessary? Clearly?
Yes.
So when you end up having a salt bridge, what is the salt bridge going to be doing? That salt bridge fellow is effectively going to be something which will, of course, end up doing what here? The salt bridge will effectively end up being something which is very useful in maintaining the balance of the charges by providing a different ion to complement. So the problem here is not that zinc 2 plus is getting accumulated. Zinc 2 plus can be here, no problem. The problem is there is nothing balancing it out. So as and when zinc 2 plus gets accumulated here, in that salt bridge, we will usually be having ions, or rather we'll have a substance like potassium nitrate, KNO3. So if I have KNO3 as my substance in the salt bridge, what is KNO3 containing? It contains K plus ions and it contains NO3 minus ions. Correct?
Yes.
So when this side is getting extra zinc 2 plus, I will have NO3 minus ions going in. As and when extra zinc 2 plus goes in, for every single extra zinc 2 plus, we will end up having 2 NO3 minus ions going in and balancing it out, neutralizing that solution out immediately. In a similar way, when I'm going to be having this side here, sulfate ion starts getting accumulated. What will go inside over here now then?
K plus.
Good. So the K plus ion will now go inside over here and will balance out that sulfate over there. You understand what's happening by the salt bridge over here clearly, beta?
Yes.
So if these two are here, what will happen? Now my voltage will work properly for a longer period of time. Yes or no?
Yes.
So in the beginning, chemistry was basically looking at studying the reaction and the voltage was important. But once it became something where there was a constant voltage available, what did scientists start realizing? At constant voltage, what starts becoming more interesting? If you're able to achieve constant voltage like this, what does constant voltage mean? Simultaneously, what does constant voltage mean? It means the bulb is glowing permanently, right? And with a
Yeah.
clean light, correct?
Yes.
So if it is going to be something where the voltage is slightly lower, what happens? The bulb will glow lower, right?
Yes.
So if we are able to get it to a constant voltage or a nearly constant voltage, we will be able to start using electricity truly. So when scientists started realizing that, what happened was all of the energy into developing electrochemical cells started going towards finding cells and making them. What should be the necessary condition? What do I want in that cell which I'm going to be making or using? What do I want? If you're buying a cell, what do you want?
Constant voltage.
Perfect. This became the mantra. You understand what's going to be happening next over here?
Yes.
So things started from Daniell Cell. Daniell Cell, they basically started with the chemical reaction. They wanted to harness the chemical reaction as efficiently as they could. In the process of harnessing that chemical reaction, they realized the best way of harnessing it is converting it to electricity and using it as potential to make it do work by glowing bulb, etc., etc., etc. In that process, what they realized was, oh, from here, constant voltage is going to be far more important. That means any electrochemical cell we are going to be making is going to be something which is going to be requiring a constant voltage. Only then is it going to be something which I can sell in the market and make money. Scientists at the end of the day are people who are interested in money just like everybody else. So scientists of that time automatically moved towards what was going to be conducive for making money effectively. So the idea here is we are going to be moving into the next part of the cells over here. I hope you understand the general story as to why things move from here to the next step. Because in the remaining electrochemical cells, what do you have as a constant trend in all of those electrochemical cells? Let's quickly have a look at this. Open and board. So the topics you mentioned were dry cell, fuel cell. So let's start talking about, let me just cut this part out and stick it there. Okay. Hmm. Okay, this has been going on in a very random place over here. Okay, let's get to the next page and continue on. So when you're going to be having the remaining cells taken, most of the time you will end up having the cells having constant voltage being what we are predominantly aiming for. Let's start with a dry cell and a fuel cell. I suppose you understand what are cells in general now, yes, Kana?
Yes.
And what is the purpose of these cells and how they are basically utilized, and what is Nernst equation? Nernst equation is basically going to be giving us mathematically how we can what to say, understand or link up the different variables which we have, which we can calculate. What are the different variables which we can calculate as what to say, scientists who are studying this? We can effectively calculate stuff like, say, for instance, we can calculate what is the concentration present in each of the containers. We can calculate what is the voltage, and then see what connects all of them. So that is basically going to be your Nernst equation over there. How electrode potential is changing with concentrations. That is basically what it helps us in understanding. So it also helps us in connecting what is going to be the other way of understanding tendency of a reaction to happen. So when we are looking at tendency of a reaction to happen, we started off with that only. So let me give you three different ways in which tendency of a reaction to happen is measured or is understood by us. So tendency of a reaction to happen is something which can be measured. Theoretically speaking, one way is going to be delta G. One way of quantizing it is delta G. Another way of quantizing the same thing is going to be equilibrium constant. Another way of quantizing the same thing is going to be electrode potential. And then yet another way of quantizing it is going to be the one which is going to be the one which is linked to the electrode potential, which is tendency, which is the definition of electrode potential actually. So let me just put it closer to electrode potential. This is actually definition of this, which is going to be tendency for, or other willingness of electrons, tendency for flow of electrons. That is effectively the idea here. So each of these three are basically measuring the same thing, the tendency of a reaction to happen. That is what they are measuring. So ultimately, since they are measuring the same thing, we need to have some way to connect all of them together as well. Do you understand what's happening over here, Kana?
Yes.
So effectively, the idea here is what we are trying to study is we are trying to study a chemical reaction. So I want to define, or I want to understand the tendency for a chemical reaction to happen. So how do I understand the tendency for a chemical reaction to happen over here? The way to understand it is I will have to, what to say, different scientists took different paths of understanding. One scientist went into delta G aspect of it. They understood a different way of looking at it based on heat. Another person basically went into the equilibrium part of it. And yet another bunch of people went into the, what to say, control of it. And they basically ended up having one more way of quantizing the same thing, electrode potential. So each of these is basically a way of quantizing the same thing. So what are we trying to quantize over here? We are trying to quantize tendency of a reaction to happen. All of that started from there. And it started off and went into what is going to be delta G, what was K equilibrium. And from there, it directly dove into, what to say, electrode potential, which went into control. And from the control, it jumped into electricity. That's basically what happened. So let's now dive into dry cell directly. I am again getting diverted into the larger domain there. Do you understand why you have learned equations connecting each of these now?
Yes.
So the reason why you learned equations connecting each of these was because they were all studying the same thing. They were all studying the same thing. They were all trying to study the same thing, trying to do the same thing, which was quantize the tendency of a reaction to happen. So that methodology was basically done using this delta G and K. I mean, what you learn it as connection between delta G K equilibrium. What is this connection? Can I tell me the connection? What's the equation?
Um, delta G is minus NF by RTLN case.
Sorry. Delta G is equal to
Not delta G. G naught is RTLN case.
give me that. What is that? Delta G
Minus
naught is equal to
RTLN KC.
good. So delta G naught is going to be minus RT ln Kc, or in this particular case here, K equilibrium. So delta G naught works out as minus RT ln of K equilibrium. Yes, that is the one I was looking for. It looks like you are struggling for a bit, but your
Yeah, I
last
was
bit
saying this
would
stuff.
save at the ending. Nice one, nicely done. Now, how about these two over here? Delta G and the other one over here. What is the connection between these two? Electrode potential and delta G. What is the reaction here? You know this one also. Come on.
Delta G naught is minus NF E naught offset.
Good. And lastly, the reality is there will be questions sometimes. JEE में तो definitely आता है. मुझे तो तेरे question papers में तो I do not know, where they will try to link these two and ask you questions. That will basically be your Nernst equation. All right. So linking of these two is what? Nernst equation. So far from what I saw, Nernst equation, the questions are easy enough only. So they're not going to be that complicated from what I see.